Thanks for joining. I'm Daniel, and today in Rustland, we want to explore NLL or non-lexical lifetime. So recently, the Rust team announced that NLL, with the latest version of the Rust 1.63, is fully stable and will be enabled by default. But what is NLL and what does it do? To answer that, let's present an example. As you can see, we have a vector of the numbers, and then we have variable number referencing the first element of this vector, and after that we're trying to push number 4 into these numbers. In older version of the Rust, before non-lexical lifetime, this code would not compile. To verify it, I'm using Rust version 1.31 on Docker. As you can see, the Rust compiler here sees that the number is borrowed by the number variable, so it disallows further mutation of the numbers. So over here, we're trying to immutably borrow, and then try to mutably borrow over here. However, we can trivially see that this is overly conservative, simply because the number is never used. The problem here is that the borrowing of a numbers by number is lexical, so it lasts until the end of the block. So over here, when the number reaches at the end of line 7, it goes out of scopes and it gets dropped. Non-lexical lifetime enhances the compiler's ability to understand this level of details. The compiler can now more accurately tell when a borrow is needed, and this code will compile. To test it out on a newer version of Rust, let's get back to our own system and run the same code. As you can see, it compiles. Before we proceed, let's see what lifetime is. The borrow checker's main principle is that values cannot be changed or moved while they are borrowed. But how can we tell whether a value is actually being borrowed? The basic idea is that the compiler gives the reference created as a consequence of a borrow a lifetime. The duration of the code for the reference may be utilized is represented by this lifetime. The shortest lifetime it can have while still covering all uses of its reference, the compiler will infer, is this lifetime. Keep in mind that the Rust has a very specific definition for the word lifetime. The lifetime of a reference corresponding to the span of a time in which that reference is used. The lifetime of a value corresponding to the span of the time before the value gets freed, or put it in another way, before the structure for the value runs. So let's see that in action. To better understand the difference between lifetime and scope, let's consider a simple example. In this example, the vector of data is borrowed mutably and the resulting reference is passed to the function. Since this function does not return the reference back, the lifetime of this borrow will become confined to just that call. The scope of the data in the contrast is much larger and corresponds to a suffix of the fn body, stretching from the let until the end of the enclosing body. So for the capitalizer, the lifetime ends here. So with the capitalizer, the lifetime ends here. But the scope of data is valid until here. This example shows that the lifetime in Rust today are quite more flexible than scopes. A scope generally corresponds to some blocks, or more specifically, a suffix of blocks that stretches from the let until the end of the enclosing block. A lifetime can also span an individual expression. The lifetime of a borrow in the example is confined to just to the call to capitalize and doesn't extend into the rest of the block. This is why the call to data.push that comes below are legal. Today's lifetime are usually sufficient as long as the reference is only used once. However, issues emerge if your reference spans many statements. The innermost expression, which is frequently a block that includes both statements in such a scenario, is what the compiler expects to be the lifespan, and it is generally considerably larger than what it is really required or intended. Let's examine some hypothetical problems instance. We'll see how non-lexical lives resolve these problems later. So let's start by case 1, referencing assigned into a variable. We're going to use Rust version 1.31. One common problem case is when a reference is assigned to a variable. In this example, which is a variation of the previous example, you're using reference to the mutable slice, which is passed into the capitalized. So let me just arrange this file a little bit. So as you can see, you're using a slice, which is a mutable borrow from the data, and this slice is being passed to the capitalize. If you look at the lifetime of the slice, its lifetime is expanded all the way down to the end block, and it has collided with the mutable borrow of the push over here. So as you can see, it says that first of all, mutable borrow occurs here, which is the slice of data, and also the second mutable borrow occurs here, which is the data.push dot character, the one character. So how can we fix it? Well, in this case, we can wrap the slice and the capitalize into its own block. You can just simply wrap them into their own block. And now if we just check it again, it is passing. As a result, the scope of the slice is now smaller. So the lifetime of the slice is now only contains this 2 line. And when it's switching to this parenthesis, the slice goes out of scope and it's being dropped. So now we can push the characters here. Now, let's test the case 1 in the stable Rust. If you look at here, if I check my code, it says working correctly. It's not complaining about the pushes on line 11, 12, and 13. And why is that? Because over here, the NLL could successfully identify that the capitalize and the slice lifetime is going out of scope over here. So while it was incorrect, while it was not working in the previous version, now the lifetime is simply dropped over here. So now I can just simply add another characters to my data. Now, let's move on to case 2, conditional control flow. Another common problem is when a reference is only used in one given match arm. The most commonly rise around the maps. If I try to run the code, you can see that it is complaining that on line 46, I'm trying to use insert with mutable borrow, while it was previously borrowed over here on line 43. Now, a workaround for this is that I just return over here and simply move map insert out of the match. Now if I just check, if I run check, you can see it's working correctly. If I get back to stable Rust and try to run the same, you can see it's working correctly. So in here, NLL could identify that the map's lifetime was not necessarily needed here, so it went out of scope before it gets to none. Now, let's check the third case, conditional control flow across functions. While we managed to work around the previous case, there are other variations of conditional control flow that cannot be easily resolved. Let's look at the following example. And for a moment, let's pretend that entry API for map does not exist. In this case, it looks almost the same as previous example, except now the lifetime plays differently here. In some branch, The value is being returned out of the color. Since value is referenced into the map, this results that the map will remain borrowed until some point the color with tag R goes out of scope. To demonstrate it better, let's add the function here which calls the getDefault and observe its lifetime like follow. So in here, we have a map. Now, we're going getDefault. And what is happening here is that if I try to get default inline, as opposed to the previous lifetime, which was limited to the match, the new lifetime extends out into the color. So the lifetime of the value extends all the way down to here. And now it is colliding with map insert and map.getMute. Therefore, the borrow does not end just because we exited the match. As a result, when we try to call insert after the match, it is still in the scope. The workaround for this problem is to use the precise control flow of a function to determine which borrows are in the scope. We can also use entry API of map, but more on that later. So the way we can solve it, so first of all, let's check that map contains the key, and if it contains, I want to return value, and if it does not contain, I'm just going to call unreachable, because we previously checked that it should contains. And now let's just call app.insert and then app.getMute. Let's just check, and it's passing. Right. Okay, now let's go to case 4, mutating a mutable reference. We're assigning a mutable variable x after the reference x has been borrowed is prohibited by the current borrow checker. This most frequently happens when creating a loop that walks down a data structure gradually. For instance, consider this function which converts a linked list mutable list of t into vector of mutable t. So over here, as you can see, it complains that the list.value is borrowed on the push, and also it is trying to assign a borrowed item here. What went wrong specifically was that we borrowed list.value, or most specifically list.value. The present borrow checker enforces restriction on assigning to a path that has been borrowed or any of the prefixes. This indicates that you are unable to assign to any of the following in this situation. The assignment list equal n is thus prohibited. In some circumstances, such as when we cross a mutable reference, these rules are valid. For instance, if list bit of type, if the list of type is with t and not a mutable list of t. Then overwriting list will also overwrite list.value. There are various workarounds for this problem. One simply being to use a temporary variable like follow. So we can say let temp equals list, and we just want to use temp.value and temp Dot next. Now over here, we just use the list. So if I just go check, can say it's passing. Right. This solution is definitely inconvenience. Turns out that this issue is not specifically related to the non-lexical lifetime. Instead, it's because the borrow checker's constraints are overly restricted and fails to take into account the indirection that its borrow reference represents. Let's try it on a stable ROS 2. So over here, instead of just using the temp, I'm just using the list directly. So cargo check, and it's working. Very good. And that is exactly what this RFC's 2094 is trying to tweak. So you might ask, why were lexical lifetimes allowed in the first place? To answer that, first we need to understand lifetime. Rust is intended to only allow known safe programs to compile, but at the same time, it is impossible to exactly allow only safe program and reject unsafe ones due to halting problem. To that end, Rust errors on the conservative side, rejecting some safe programs. Lexical lifetimes are one of such example. Because knowledge of blocks is trivial, lexical lifetimes are much easier to implement in a compiler than knowledge of the data flow. So the compiler had to be rewritten in order to introduce and use a mid-level intermediate representation, or MIR. The borrow checker, also known as borrow CK, had to be written to use MIR rather than an abstract syntax tree, or AST. The borrow checker's rules had to be refined to be finer grained. So now let's look at Rust Abstraction Syntax Tree, or AST. To understand AST better, we need to jump into the parsing step of compilation. At this stage, a parser program within the compiler analyzes the tokens created by the lexer and converts them into abstract syntax tree, or AST. Having these tokens into a data structure makes the reminder of the compiler's jobs constantly easier and faster. The Rust compiler will now take the abstract syntax tree created by the parser at this point before processing to the next level of compilation. That is, or better say was, how the Rust compiler represented the source code. AST has nodes to represent each expression's statement, function, module, and all other bits. So how can we say it? Well, you can't, at least not directly. You see, Rust compiler's own parsing code in the library called libsyntax, and it was a private library inside the compiler. Rust team had a valid reason for it, as they did not want to deal with the breakage change of outside projects. Lucky for us, someone maintained a copy of it on crates.io, and it's called syntax, which uses the stable Rust. You can test it for yourself and see how it works. So for instance, a statement like 1 plus 2 will eventually turn to something like this. With RFC number 1211, which is about MIR, or mid-level IR, we know that Rust surface representation is mostly desugared by the MIR, leaving a more straightforward form that is ideal for type checking and translation. If you want to see how your code turns into MIR, you can use play.rustlanguage.org. So over here, we can use our previous implementation, and if you hit ellipsis over here and select MIR, you can see your code. You can see your code MIR is shown down here. So we have our main function, then we have some declarations, and also if you look at here, we have a couple of scopes. As you can see, Rust now is using different scopes for our code. This way, borrow checker would not get confused over the lexical items. So, that was all? Of course not. As promised, non-lexical lifetime were not all bad and trying to restrict us. Based on a non-lexical lifetime, powerful patterns were invented. Interestingly, several useful patterns evolve as a result of lexical lifetime. The entry pattern is a perfect illustration for us. If I come over here with case 5, imagine that a function which takes a hash map, and every time we call this hash map with a key, it's either going to increase its value by 1 or it's simply going to insert the 1 with that key. So if I just run cargo check, of course I need to use steady collections hash map. Okay. As you can see, this code fails on previous rows. Now let's try to run it on a stable version. As you can see, it's passing. But you may have noticed that this code is not optimized, since it's calculating the hash of the key twice, one over the getMute and one in here over insert. Because of the lexical lives, the solution is shorter and more efficient. We can simply replace this code with star map that entry key or insert 0 plus equal 1. This way, the calculation of hash key is only done once and is more optimized compared to this one. Now, if we get back to problem case number 3, we can solve this issue with following code. So instead of that, I will simply use map.entry key dot or insert with closure the default. And that's all I need to do. So we have a new generation of borrow checker. It is worth mentioning that the Rust team is now working on a new generation of borrow checker called Polonius, which can handle more cases of NLL and distinguish borrowing from lending. So Polonius is effectively an NLL 2.0-like project, and it aims to achieve 2 goals. Number 1, improve upon the borrow checker algorithm so that it can accept more Rust programs that it currently does. And 2, move the core logic of borrow checker into the independent crate, whose behavior can be easily tested and specified. If you need more information or you want to get involved, you can check the following links. So how can I use NLL, an older version of the Rust? So starting from Rust 1.31, simply by changing your edition to 2018, you can opt in using NLL. With previous version of Rust, before 1.63, as the implementation of the non-lexical lifetime was still in migration mode, if the NLL borrow checker passes, compilation continues. If it doesn't, the previous borrow checker is invoked. If the code is allowed by the old borrow checker, only a warning is printed, informing you that your code is likely to break in the future version of the Rust and should be updated. To enforce breakage on nightly builds, you can have used the NLL feature flag. So you can actually, at the beginning of your code, enable the feature NLL and you're opting. As of 1.63, NLL is fully stable and enabled by default. So hopefully you can see why the following code fails and what the workaround is. Now, if we get back to our code, we run cargo check. You'll see that it's complaining that wick push is mutably borrowed, and again, immutably borrowed on line 148. So one of the workarounds for this is that we use if vec dot is empty equals false, and we just wrap it around here instead of iflet. And simply return the vec dot last dot unwrap. Now if you check it again, see it's passing. And that's it. If you have any question, write it down in a comment, please. Also, don't forget to like, subscribe, and hit the bell to get the notifications on the new videos. Thanks for watching, and I will see you on the next one.